And I guess so most speakers live in the US, so oftentimes they also switch back. So the talks are kind of in Russian, but then when it comes to some, I don't know, Kpz equation type of terms, they would anyway switch to English.
They haven't been right. I mean, a lot of the contemporary stuff, like less than 10 years old, probably doesn't have a Russian version yet.
Yeah, presumably.
I don't know, what would the directed landscape be, or the stochastic area operator?
Okay, I think stochastic area operator is easier, right? Just
oh yeah, because operator and stochastic, yeah.
Yeah. Yeah, landscape, I'm not sure what the appropriate term would be. Directed is probably направленный. But yeah, landscape, I don't know, maybe направленная поверхность.
Поверхность.
I guess let's give it a minute. All right, Evgeni, if you're ready, let's get started. So yeah, I'm very happy to introduce you. And Evgeni will be talking about characterizations of Gibbsian line ensembles. Please.
So thank you very much for the introduction and the invitation. It's certainly a great pleasure to be giving this talk. So today I will discuss a couple of recent results that provide a characterization of Gibbsian line ensembles. So first, explain kind of a zero temperature version of this story, where the objects are called Brownian Gibbsian line ensembles. So I'll tell you what these things are. I'll give you a few examples of such objects, and then I'll tell you a classification result for them. And then I'll formulate the positive temperature version of the story. And in the end, I'll explain kind of how these characterization results fit into a sort of general framework for establishing Kpz universality for line ensembles. So first of all, what is a line ensemble? So a sigma indexed line ensemble on an interval lambda is just a collection of random continuous functions that are defined on the same probability space. So these functions are labeled by an index set capital sigma, which for the purposes of this talk would be just some set of consecutive integers starting from 1, which could be either finite or it could be infinite. Okay, so in plain terms, a line ensemble is just a finite or countably infinite collection of random continuous functions on the same space. As a simple example, we can consider the case when sigma is the set 1, 2, 3, lambda is the unit interval, and then three independent standard Brownian motions form a line ensemble with 3 lines. And this is how it looks like. So the next thing I want to define is what is the partial Brownian Gibbs property. So we say that a line ensemble L satisfies this Gibbs property if it satisfies the following 2 conditions. So the first condition is just that the curves of your ensemble need to be strictly ordered. So L1 needs to be strictly above L2, strictly above L3, and so on. So if you kind of draw them on a picture like this, they need to be strictly ordered downward. And then the second condition is that for any finite number k, which is less than the total number of lines in your ensemble, you want the local distribution of the top k curves to be described by avoiding Brownian bridges. And so one way to think about this second condition is that you want the law of your ensemble to be invariant with respect to the following resampling procedure. So you first start by sampling your line ensemble, and then you get something like this, and you fix 2 times little a and little b. And then you erase the top k curves from your ensemble between these 2 times, and then you arrive at the picture like this. And then you proceed to fill in the gap. You sample k independent Brownian bridges that connect the red dots that are independent but conditioned to avoid each other and also avoid the k plus first curve here. And then you fill in the gap. And in this way, you obtain a new line ensemble. And the essence of the Gibbs property is that the law of this new ensemble is the same as the one that you started with. So it's invariant with respect to this resample. Now the word partial in this definition has to do with a special role that is played by the bottommost curve, Ln. So in this setup, this curve plays the role of a bottom boundary for your ensemble. So it could be deterministic, it could be random, but it's not necessarily invariant with respect to the previous resampling procedure. Now, if it happens to be the case that the bottommost curve can also be resampled in the same way, or if the number of lines is infinite, meaning there is no bottommost curve, then you drop the word partial and you just refer to this as the Brownian Gibbs property. And this was a term that was coined by Corwin and Hammond. So here I'll give you a few examples of Brownian Gibbsian line ensembles. So kind of the simplest situation is, suppose you have kind of, you fix a continuous function f, a deterministic one, and you set your bottommost curve to be equal to that, and then you sample a bunch of independent Brownian bridges. So imagine everything is on the unit interval, and you just sample independent bridges that are conditioned to avoid each other and also stay above this bottommost curve f. So that's an example of a Gibbsian line ensemble. A more complicated example is given by Dyson Brownian motion. I'll just remind you that Dyson Brownian motion is just a collection of n standard Brownian motions that are all started from the origin, but are appropriately conditioned to never cross for all positive time. And this is another example of a line ensemble that satisfies this Brownian Gibbs property. Our third example is given by what's called the parabolic airy line ensemble. And this is obtained through an edge scaling limit from Dyson Brownian motion, for example. So if you start Dyson Brownian motion with n curves and you increase the number of curves to infinity, there is a way to appropriately shift and scale this ensemble at the edge to obtain a non-trivial limit, which is called the parabolic airy line ensemble. And this one is a line ensemble with infinitely many lines, but it still enjoys the same Gibbs property. Now, the questions that we want to understand is basically how much information do we need to specify the law of a Brownian Gibbsian line ensemble? And to sort of motivate this, the result in this direction, I'll discuss an example that I like to call the princess and the pea. So the setup is as follows. So you have 2 beds. One of them has a perfectly flat base, and the other one has an almost perfect flat base, except that it has a small aberration, aka the pea. Now you start piling a bunch of matrices on top of the 2 beds, and you can put different number of matrices on the different beds. And and these matrices can have their endpoints are the red dots here, and they can be deterministic, they could be random, they can be whatever you want, except that you demand that the conditional law of the matrices given the endpoints should be that of avoiding Brownian bridges connecting the red dots that avoid each other, but also the base, or in this case, the base and the P. Now, a keen observer, aka the princess, observes the top curves of these 2 line ensembles. So she sits on both of the beds and she feels the top matrix of each one. Now, she doesn't interact with any of the bottom matrices, but she's very sensitive. So by simply sitting on the two beds, she can determine everything there is to know about the law of the top curve. And then the question is, based on this information, can the princess distinguish between these two beds? That is, can the princess feel the P? And the answer is yes. And in fact, she can determine much more than this. By simply observing the top curve of this ensemble, she can determine the entire joint law of all curves together with the base. So in particular, she can tell if there's a P or there isn't one.
Evgeni, she feels the law. She only tells one sample path of the top mattress, or she can tell the law.
So this is not a statistical inference question. So she knows the law of the top curve. So it's not like she gets one sample and based on that she can say whether there is or there isn't a P. So you should imagine that she has infinitely many samples of the top curve.
Okay. I mean, these are continuous time curves, so there could be a lot of deterministic information contained as well. But
oh yes,
you see the whole law, right? So
yeah, yes.
Okay, good. Just
as I said, she is very, very sensitive. Beyond imagination. So this is a fairy tale. But anyway, so hopefully it's clear what I meant. And if not, the next result will say precisely what I mean. So the statement is as follows. So this is a theorem by myself and Konstantin Matietsky. And the statement is, suppose you have two line ensembles, L1 and L2, and they both satisfy the Brownian Gibbs property. And suppose furthermore that the top curve distribution of the first ensemble has the same finite dimensional distributions as the top curve of the second ensemble, then you can conclude that the full ensemble laws need to match. So in plain words, what the theorem says is that a Brownian Gibbsian line ensemble is completely characterized by its top curve distribution. And I won't go into the proof, but I'll mention that the proof is non-constructive, meaning that even if you have a Gibbsian line ensemble and you give me formulas for the top curve distribution, I can tell you there is a unique possible law for the second curve, but I can't give you formulas for it. So it's kind of a uniqueness proof rather than a constructive one. And so the last thing that I'll mention is that this kind of an immediate corollary of this theorem pinpoints the parabolic area line ensemble as the unique line ensemble that has both the Brownian Gibbs property and the parabolic area process on the top. So the top curve and the Gibbs property uniquely pinpoint this object. So the next thing I want to do is I want to give you a positive temperature version of this result. But in order to do that, I need to give you a little bit more information, more notation. So here what I want to do is I want to define what's called the H Brownian Gibbs property. So we say that the line ensemble satisfies this property if the conditional law of any k consecutively labeled curves is the law of k independent Brownian bridges whose distribution has been reweighed by the following Radon-Nikodym derivative. So this is not a complicated formula, but let me try to explain what it means. So first of all, the curves behave like independent bridges, but they have an interaction that is reflected in the distribution through this reweighing. And the interaction is encoded by this function capital H that I like to call an interaction Hamiltonian. Now, the argument of this interaction Hamiltonian is the difference of two consecutively labeled curves. So the first thing to observe is that the indices of these curves are consecutive, meaning that curves that are whose indices are two or more away from each other don't talk to each other. So the interaction between the curves is local in the index. In addition, the fact that the argument here is both U means that the interaction is spatially local. And so this thing is supposed to be kind of a recipe for constructing a Gibbs property that has local in space and in index interaction of the curves. And just to relate this to the previous part of the talk, so if you pick the function h to be the function that is infinity for positive values of x and 0 otherwise, and you look at what is this Radon-Nikodym derivative going to do. So this is formally plugging it in. So if the difference here is positive, what it means is that the I plus first curve overcame the ith one, so it's higher than it. And any such path configuration is going to have a weight that is e to the minus infinity, so that's a 0. If the curves are strictly ordered, then these differences will all be negative, and so all of these integrals are going to evaluate to 0. So you'll be reweighing by e to the minus 0, so that's a 1. So the effect of reweighing by this Radon-Nikodym derivative is that it kills the weight of all path configurations that go out of order, and it keeps the weight of all path configurations that are in order, which is exactly the same as kind of uniform conditional on avoidance. hopefully that's clear enough. Now, another natural choice for the interaction Hamiltonian is given by basically taking an exponential function, e to some positive constant times x. I'll explain in a moment why we take this constant to be t to the 1/3. But first, this gives you a one parameter family of interaction Hamiltonians, and the way that I like to think about it is that this family interpolates between complete disorder and complete order as t varies from 0 to infinity. So if t is equal to 0, this function is going to become identically equal to 1. So it's a constant function. And then this Radon-Nikodym derivative is going to become constant. Now, if you weigh a probability measure by a constant Radon-Nikodym derivative, you leave the law invariant. So the law stays the same as that of independent bridges. So the bridges can go out of order, they're independent. On the other hand, this t tends to infinity, this function exactly converges to this one here, so that the paths become strictly ordered. So as t varies from 0 to infinity, you go from complete disorder of the paths to a strict ordering of the paths. Now, a remarkable result that was established by Corwin and Hammond was that there exists an infinite line ensemble that satisfies this H Brownian Gibbs property with this interaction Hamiltonian H. And this is what's called the Kpz line ensemble. And it's one of the universal scaling limits in the Kpz universality class. So I won't give you a definition, but I'll tell you a little bit about its features. So first of all, it's kind of a positive temperature analog of the parabolic area line ensemble. So in the former, the paths were strict. In the latter, the paths were strictly ordered, whereas in the Kpz line ensemble, they can go out of order. So as the picture indicates, the paths can break their order. Now, every time the paths break their order, that comes at an exponential energetic cost. So even though they're allowed to do this, and they do it occasionally, they like to stay in order as much as they can. Now, the other thing that I want to mention is that in the parabolic area line ensemble, the top curve plays a distinguished role. Up to a shift, it's given by the Airy process. And here, the lowest index curve L1 also plays a distinguished role. Its distribution is nothing but the solution to the Kpz equation at time t started from narrow wedge initial data. So that's why we have this t to the 1/3 here, basically to ensure that the top curve is the time t solution of the Kpz equation. Okay, so this is a positive temperature version of the previous story, and naturally we would be interested in establishing a positive temperature classification as well. And so that's the next theorem. So the statement is similar as before. So suppose you have two line ensembles L1 and L2, but now they both satisfy the H Brownian Gibbs property. And you again assume that the top curves or the lowest index curve of these two ensembles have the same finite dimensional distributions. And you can conclude that the laws of these ensembles are the same. And that's under certain conditions on the interaction Hamiltonian H. So we want this interaction Hamiltonian to be a convex function. And also you want it to satisfy some complicated looking statement, which basically means that you want your function capital H to grow like an exponential function near infinity. So for some positive lambda, you want this difference to kind of near infinity go to 0 in some uniform sense. So for example, if H is exactly equal to an exponential function, this is equal to e to the lambda x, this ratio is going to exactly cancel for all x, and this statement will be satisfied. But we can handle slightly more general interaction Hamiltonians. So in plain words, what again the theorem says is that an H Brownian Gibbsian line ensemble is completely characterized by its lowest index curve. And in particular, it says that the Kpz line ensemble is the unique H Brownian Gibbsian line ensemble that has this interaction Hamiltonian and the narrow wedge solution on the top. Okay, so these are the two classification results. And the next thing I want to explain is why do we care about these types of statements? So in general, there's various people that are interested in understanding Gibbsian line ensembles. So there's kind of beautiful conjectures about classifying these objects. Now the theorems that I presented don't really address these conjectures, but they further our understanding of Gibbsian line ensembles in general. Now the second sort of point of interest that is the one that I'll describe here is that these theorems pave a route to establishing Kpz universality for line ensembles. So some of the questions that I have been thinking about involve dealing with some sequence of discrete line ensembles. And what I mean by discrete line ensembles, you should visualize some large number of avoiding random walkers. And what we want to understand is when can we establish convergence of these avoiding random walkers to the, let's say, to the parabolic area line ensemble. And in fact, we're going to be ambitious. We're not just going to ask for kind of finite dimensional convergence of these objects. We're going to ask for some strong notion of convergence, which is in the topology of uniform convergence over compacts. And so the framework that I've proposed consists of establishing the following two steps if you want to answer this question. The first one is kind of getting some qualitative information about your sequence of ensembles. So you want to show that that sequence is tight and that all subsequential limits satisfy the Brownian Gibbs property. So again, typically you're dealing with something that locally looks like avoiding random walkers, which formally in the limit should look like avoiding Brownian motions. So you're not really after some precise statement here. You're rather interested in establishing some qualitative features of your sequence. You still need, however, some type of quantitative control, and that is the second point here. So in the framework, you want to show that the top curve of your discrete line ensemble converges in the finite dimensional sense to the parabolic area process. Now, if you have these two conditions satisfied for some sequence of discrete line ensembles, then condition one will tell you that your sequence is tight. So you have subsequential limits. And moreover, for any subsequential limit, you note it has two properties. The first one is that it has the Brownian Gibbs property. And the second one is that it has the parabolic area process on the top. Now, the previous theorem that I mentioned tells you that there is a unique object that has these two properties, namely the parabolic area line ensemble. So all subsequential limits have to be equal to it, which together with tightness implies weak convergence. So the benefit of this framework is that it reduces the amount of quantitative information you need to control from the full ensemble to only the top curve, meaning you don't need any formulas for the second or so on curves to establish weak convergence. And just to illustrate kind of how this framework works, I'll mention a kind of a result that we worked out last summer during an REU with these students. So the setup is as follows. So suppose we have a sequence of avoiding Bernoulli random walkers. So you have for each capital N avoiding Bernoulli random walkers that start from some random initial configuration and end at some random initial configuration. But inside they evolve like independent Bernoulli random walkers that are conditioned to avoid each other. Now suppose further that you know that under suitable shifts and scales, the top curve, so this top line here, converges in the finite dimensional sense to the parabolic area line ensemble. So based on this, you can conclude that under the same shift in scales, even though it's not denoted here that you need to rescale all the curves, not just the top one, the full ensemble is going to converge to the parabolic area line ensemble in this uniform sense. So kind of what this is saying is that if you have a sequence of curves which converge to the parabolic area process, and those curves are embedded as the top curve of a bunch of Bernoulli Gibbsian line ensembles, then in fact, this Gibbs property improves the convergence from finite dimensional to uniform, and also from the top curve to the full ensemble. So there's kind of two levels of improvement. Now in the proof, we don't really rely too much on this finite dimensional convergence. So kind of, in general, you want to show that your sequence of ensembles is tight, and then this finite dimensional convergence is only using the previous theorem to pinpoint the limiting object. And in fact, to prove tightness, we need quite a bit less than that. So not only do we not need any finite dimensional convergence at all, we just need 1 point convergence at best. But in fact, we can even reduce that to not even require any sort of convergence. We can do it with kind of 1 point tightness plus some sort of uniform parabolic behavior of the curve. And the other thing I want to mention is that in a kind of follow-up work to this one of the authors, Christian Serio, in his senior thesis has extended this result to not just Bernoulli, but kind of generic random walkers. So there's some technical conditions that I'm not going to go into, but he can handle things like geometric jumps, Poisson jumps, uniform on some compact integer interval jumps. There's kind of a large family, but it's not everything that you can imagine. So the framework, at least kind of what I tried to explain, is that it can be used to understand scaling limits of avoiding random walkers. Now, there's various other applications of the framework, and the ones that I'm interested in personally come from applications to models that originate from the McDonald processes that were introduced by Borden and Corwin. So specifically, there is some partial work that I've been involved in for applying this framework to models of whole-little plane partitions and for the log gamma polymer. But it's not complete. So we're after this sort of uniform convergence to the ensemble, but we have partial results in that direction. And the last thing that I'll mention is that the framework I formulated it for the parabolic area line ensemble. You can replace everywhere here this line ensemble with the Kpz line ensemble and play the same game. And in fact, it appears that the 2 points that are here have been basically follow from the work by Xuan Wu. So this is her PhD thesis. So it's not published yet, but presumably once it's cleaned up, one can use it to basically deduce these 2 points. Okay, so that's what I wanted to say. Thank you very much for your attention.
Thanks, Evgeni. So any questions? So maybe I'll ask a good question. So you mentioned in the Kpz line ensemble, you have this nice property that the top curve solves the Kpz equation. In the parabolic area ensemble, is there a nice description of the top curve that one can use kind of together with your results to get this convergence?
So I think there's 2 questions. The first one is, does it have a similar type of a description in terms of a solution of some equation? And what was the second one?
Right. Yeah. So basically, what you need kind of as an extra input in your convergence result is to be able to show that you converge to the top line, right? Mm-hmm. So you need some sort of either equation or characterization of the distribution of the top line.
Well,
to know what you want to converge to.
Right. So well, okay. So first of all, the top curve, which is the parabolic area process, one way to think about it is that it's the time one distribution of the Kpz fixed point, and this there is a paper by Castel and Sarkar that kind of utilizes this type of statement to show, for example, that the ASEP converges in the finite dimensional sense to the Airy process. And in fact, the ASEP, this is a result by one can embed the ASEP height function as the top curve of a Gibbsian line ensemble. This is something that we did with Ivan in 2017, so some time ago.
But this kind of undoes your trick here, right? So your trick is not to go through a line ensemble to prove convergence, right?
Right. So that's a very roundabout way of establishing this finite dimensional convergence. So I can tell you that in the models that these coming from McDonald processes, there's ways to obtain finite dimensional formulas using the McDonald difference operator. So this is a work for the whole little with the plane partition model that I mentioned. This is last year I established kind of 2-point convergence using difference operators of the top curve, and I'm currently working on kind of lifting that to kind of finite dimensional convergence. For the log gamma polymer, there's also some hope, because that one is obtained through some diffuse limit from the Q-Whittaker process. And so if you can play the same game there using McDonald's difference operators, you will have some access to finite dimensional convergence that way. Now, these are, of course, integrable models. If you have a generic collection of random walkers, avoiding random walkers, you don't have this at your disposal. So there one needs to think more. But something that I also want to mention is that there is this work, recent work by last year by Balint. Basically, it appeared the same month as Jeremy's work. They have a different way of kind of understanding the top curve distribution by kind of looking at 1-point marginals, but they need to complicate it to explain. But there is some hope of maybe doing this for polymer models as well, is what I'm going to say. So it's not clear, right? I mean, the framework is still under construction. There's all sorts of things to work out. For avoiding random walkers, I think the question is very much open. Like, none of these techniques really apply there. But depending on the context that you're working in, there are various things that one can try to do if you're in a good situation.
Right. I mean, obviously having some sort of evolution equation, that's the optimal scenario, right? Because when we prove convergence of stochastic processes, we usually go through some, martingale problem or something like that, and normally don't study finite dimensional distributions.
I mean, in a very real sense, the model that I'm describing, you should think of it as a kind of a stationary model. These line ensembles arise in lozenge tilings, for example, and you don't really have a dynamics. I mean, you can put dynamics, but that's not at least how I think about the problem. One can try to do it this way, but I haven't really thought about it in this way. But I agree. What you're describing is perfectly a reasonable thing to do.
Great. Other questions for Evgeni?
I have one.
Go ahead.
So Evgeni, great talk. I really enjoyed it. Thank you. I'm curious, the assumption that you put on the potential and the positive temperature result, is that conceptually essential, or do you anticipate this is more technical?
So the convexity is more up for debate, but this one here, to me at least, is essential, at least for the argument of the argument that I have. So in the way that the theorem is proved is kind of an inductive argument where you start from the top curve and you show sequentially that the next curves have to have the same matching laws for the two ensembles. Now, the way that you do this is you build observables that are measurable with respect to the top curve and somehow probe the second one. Now, the particular observables that I have rely on basically this type of a ratio asymptotically as y tends to infinity to satisfy the functional equation for the exponential function, that f of a times f of b is f of a plus b. Now, what's possible is that if you have a different type of interaction Hamiltonian, that you can come up with different observables that are not the same as the ones I have. I thought about it and I couldn't come up with something on the spot, and so I decided that this is a good enough result, and I didn't really push it enough. But I think that it's possible if you have kind of another. I mean, honestly, it's hard to probe general Hamiltonians because there are not many examples of line ensembles that have them. But if you have a particular Hamiltonian one can try to look at some observable that would be a natural candidate. So to me, here the natural example was the Kpz Line Ensemble, where h was a exponential. So I wanted to make an argument that works for exponential functions, not for anything under the sun. But if you have a particular interaction Hamiltonian, one can think about the other possible observables.
Great, thanks very much. That's helpful.
Right. I'm sorry to cut this very interesting discussion a bit short. So we will be moving on to Fan Wei. Fan, are you there?
Hi, yes, I'm trying to share the screen.